On calculating the mass of a black hole. A change in momentum and net force both have perpendicular and parallel components, which can be useful when performing calculations for curving motion. Change in direction comes from a change in the force perpendicular to the instantaneous momentum, and change in magnitude comes from the force parallel to the instantaneous momentum. This uses a n-hat, p-hat coordinate system, with n-hat pointing inside the circle, which corresponds to the perpendicular component, and p-hat parallel to the circle, which corresponds to the parallel component. Here are some relevant equations which we will use to perform our calculations. So the objective of this lab is to explore how to determine the mass of a black hole from the motion of an orbiting object. Because gravity is the only force acting upon the object's position over time can be used to determine the mass of the object it is rotating around using the formulas discussed before. This principle is very applicable, and we're interested in this because scientists often have to use known variables and formulas to determine the unknown, especially in space when many objects cannot be seen or directly observed. So here's the video of the prediction of the object's motion. So this simulates the star orbiting the black hole with the star as the yellow object moving in an ellipse and the black hole in the middle. And as we can see, the values are displayed at the bottom, and these arrows show the components of the force. So here's all the code for reference, but it will be explained more in depth. So here we can see that the gravitational constant was set to 6.7 times e to the negative 11th. The mass of the star was 2 times 10 to the 30th kilograms, and delta T was 86,400, which is the amount of seconds in a day, because that was the time between position checks, and the initial time was 0. And here we have the initial and final momentum, which is mass times initial final velocity. The change in velocity is the final velocity minus the initial velocity, and the change in momentum is the final momentum minus the initial momentum. And dp over dt is the change in momentum over the change in time. And using the momentum principle, we know that net force equals dp over dt. And here we are calculating the unit vector, or p hat, by doing the initial momentum over the magnitude of the initial momentum, and we use that to determine the parallel component of dp dt, which we can also set equal to f net parallel because of the momentum principle. And here we calculate the perpendicular component of momentum using dp dt perpendicular plus dp dt parallel is equal to dp dt. And so here we calculate the perpendicular component of net force, and using the law of universal gravitation, we know that the gravitational constant times m1 times m2 over r squared is equal to the net force, and once we rearrange for m2, we can solve for the mass of the black hole. So our results showed that the mass of the object was approximately 2.7 times 10 to the 64th kilograms, and the arrows that represented the perpendicular component of the force point towards the center of the circle, or n hat, which is what we expected, and the arrow that represented the parallel component of the force was parallel. And the net force in the middle of these two, or the sum of the two arrow vectors, and the star followed an elliptical orbit around the black hole, which is typical of objects orbiting. So what does it mean? So the difference between net force and its parallel and perpendicular components, and the rate of change of momentum and its parallel and perpendicular components. So net force is the sum of all the forces, while change in momentum is the change in instantaneous velocity at that time. So the components are of the sum of all forces versus the change in velocity, and the velocity and force are both vectors, so they have magnitude and direction, and the perpendicular component controls the direction for both, while the parallel component controls the magnitude for both. And if the black hole that the mass was determined of was removed and a different black hole was placed in the same position, and the motion of the star remained the same, and we knew that it was only affected by the gravitational force of the black hole, we would not be able to tell the difference, or tell that there had been a replacement, because the mass was determined using solely the position or path and the mass of the star. So if those aren't changing, then we would not be able to calculate a different mass or be able to tell that a change had occurred.